going to talk about energy. Energy is a thing that we measure in joules, 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 capital J is the abbreviation. So that's the unit that we use. I'd say something has 20 joules of energy. It's the ability to do work. It's going to become a lot clearer when we do this because there's a little bit of a chicken and the egg business in the definition. Well, what's work? Well, work is a transfer of energy. So, depending on what you define first, the other one's defined in terms of that. Energy can't be created or destroyed. There's a quantity of energy. If a system has a certain amount of energy, the only way its energy will change is if somebody does work on it, adding energy to the system, or does negative work, taking energy out of the system. Okay? And there are so many different kinds of energy. There's chemical energy, and there's kinetic, and I don't really want to talk about potential yet. But there are all sorts of different kinds of energy, and this energy is always transferred from system to system. Another system too, okay, I'll call it. So work transfers energy from one system to another. We will sometimes say that this system does so much work on this system to get it out, okay? So if we think of what energy, I do work during the day. How do I do work? And I'm going to work backwards on this. Okay, I chop wood, okay? I increase the kinetic or motion energy of the wood. Well, I did work on the wood. And therefore, I transferred energy from me to the wood. Well, the energy from me, of course, if I chop wood all day, you're tired. You have transferred a lot of energy out of your body. Where did that energy come from? Energy came from the muscles. What happened is my muscles actually burnt fuel. It was a chemical reaction that moved my muscles. That was transferred out of stores that I had in my body, food and fat and things like that. So energy is constantly being transferred from one system to another, and one form of energy sometimes to another. We're going to talk an awful lot in this unit about potential and kinetic energy. Potential is not a real energy. It's another way of measuring work in a way that makes it a little easier for us to solve some problems. So let's get right into that. What kinetic energy is. Kinetic energy is a real type of energy. If an object has motion, it has kinetic energy. Anything that's moving has kinetic energy. There are actually some other kinds of kinetic energy, but we're going to be talking about a thing called translational kinetic energy. You may not even hear me say that ever again, translational. We're just going to be talking about kinetic energy. And kinetic energy is a very straightforward concept, okay? Because kinetic energy has to do with motion. And an object has kinetic energy if it has a mass and it is moving. And the equation that we use for this is Ke equals 1/2 times m times v squared. So it's a fairly straightforward thing. The one thing I would have you take note of is this squared. Okay, if I make the mass bigger, the kinetic energy gets bigger. But if I make the velocity bigger, the kinetic energy gets much bigger. Let's take a look at that. Here's mass, here's kinetic energy. It's linear, right? Let's just say I've got something with a velocity of 1 meter per second. Okay? An object that has 1 kilogram will have 1/2 times 1 times 1 squared. The kinetic energy would be 1/2 joule. If I have something that's 2 kilograms going at 1 meter per second, the kinetic energy would be 1/2 times 2 times 1 squared, and that would be 1 joule. So I made this is for a 2 kilogram object going 1 meter per second. This is for a 1 kilogram. So I doubled the mass and it doubled the kinetic energy. It's linear. Okay, makes sense. Okay, so if the velocity is held constant, kinetic energy is linearly related to the mass. But that's not the way it works with velocity. Let's do this. An object with a mass of 1 kilogram. And let's say the velocity, again, 1 meter per second. And we found out the kinetic energy was 1/2 times 1 times 1 squared is 1/2 joule. Now, if we double the velocity, 1/2 times 1 times 2 squared, that's 1/2 times 4, is 2 joules. Look at that comparison. I doubled the velocity, but the kinetic energy is 4 times as big. If I triple the velocity, what do you think it's going to be? It's going to end up being 3 times as big, because that 3 gets squared. And we can do that for anything. Let me do 5. If I had a kinetic energy, certain kinetic energy, and I make the velocity 5 times as big, you can think of my new kinetic energy, I call that Ke prime, would be Ke times 5V, quantity squared. That 5 gets squared. So you end up with 5 squared is 25 times my old 1/2 mv squared. That's called a parametric consideration. That's called a parametric analysis. In other words, if you ever hear a question where you say, my kinetic energy is 8, what happens if I triple my velocity? They're talking about this kind of thing. If you only change one thing, what happens? And when you see this squared, if you triple this, 3 squared makes it 9 times as big. If you 4 squared, 16 times as big if you have 4 times as much velocity. So kinetic energy, and I ought to draw this, velocity, kinetic energy, goes up massively. Those of you that are taking driver's ed, you know that stopping at 10 miles an hour to stop the car requires much less energy release, much less braking distance than stopping from 20 miles an hour. You're only going twice as fast, but your kinetic energy is 4 times as big. You have to transfer out that much energy to the friction, to the braking, to the heating of the pavement. So kinetic energy, very, very important thing. And that's a real kind of energy. How do we use it? Well, we use it just the way I kind of showed. We've got 3 variables: kinetic energy, mass, velocity. If I have a car, has a mass of 1,000 kilograms, and it's got a kinetic energy of 45,000 joules, what's the velocity? Well, that's pretty easy. Ke equals 1/2 mv squared. 45,000 equals 1/2 times 1,000 times v squared. We divide by 1,000, we get 45 times 2, we get 90 equals v squared. And I don't know how to do that in my head, but square root of 30 would be the velocity. Square root of 90 would be the velocity in meters per second. Okay? So very simple stuff like that. Just 2 variables that you know, 1 variable that you have to solve for. That's pretty straightforward. The parametric, I want to take a second to talk about that parametric. Parametric means what happens if I double this? What happens if I triple this? Okay? And what I always think of with this is I write the equation. Here, let me write down what that question might be. A car has a kinetic energy of 1,000 joules. What happens to the kinetic energy if velocity triples? Okay, notice they didn't give you a mass here. What you could do is you could say, well, let's see, 1,000. Let's plug in some fake numbers that will make that 1,000. That's kind of a pain. Okay. The way I look at it is this: the kinetic energy was 1,000, was 1/2 mv squared. When they ask a question like this, I don't even use numbers in there yet. I just say, okay, so my starting kinetic energy is 1/2 mv squared. My new kinetic energy, what will my new kinetic energy be? Well, it's going to be 1/2 times, well, the mass isn't going to change, but the velocity is now 3 times as big. Okay, so I substitute 3v in instead of v. So my new kinetic energy is going to be 1/2 times m times 3v quantity squared. Then I multiply that out, 1/2 times m times 3 squared is 9v squared. And then I say, I want it to look like this. So I'm going to bring that 9 out front. So you can see this is the old kinetic energy. So whatever my old kinetic energy is, it's now 9 times as big. And that's how we do these parametric problems. I'll show other ways of doing parametric problems in the future. There's an approach that I call fake numbers. Plug in 1, pretend you're in the lab. 1 times 1, you'd have 1 times 1 times 1/2 ends up being 1/2 joules. So if the mass is 1 and the velocity is 1, the kinetic energy is 1/2. What if we plugged in 1 and 3 times that? M equals 1, V equals 3. The kinetic energy is going to be 1/2 times 1 times 3 squared, which ends up being, kinetic energy is 4.5. So this is 9 times this. You can think of this as 9 halves, 1/2. So we know that it goes up by a factor of 9. So that's an introduction to parametric problems. You could do that with anything. It's not specific to kinetic energy. We're going to do it with gravitational force later. But there's the basic concept of kinetic energy. It's a very, very straightforward concept, very easy equation. I definitely want you to be aware of that squared, and I want you to know that that means that increase in velocity makes the kinetic energy go up much more. Okay, and then the next lesson we're going to do is I'm going to talk about potential energy, and that'll be an introduction to conservation of energy.